Likewise for the other operators. If I do this really step by step, it becomes not P or Q, or not Q, or not P. I hope there are no more mistakes here. That was step one. Push negation inwards. Here we see one case where we have to push negation inwards because it's not on the literal level yet. And here you can apply the Morgan's law. And again, if I do this really step by step, it becomes not P and not Q. Yeah, so that's the Morgan's law applied to that part. Then the rest already is in the right shape because negation is already at the level of the literals. Next step, get rid of double negation. Indeed, there are two cases of double negation, which are P and not Q, or Q or not P. And finally, what do we have to do? We have to make sure that the AND is all the way outside. And that means to distribute this to distribute this OR, and this one also, over the AND. So essentially we have to copy this part, and it becomes P or Q or not P, and not Q or Q or not P. And that's all she wrote. Now this is disjunctive, this is conjunctive normal form. I'm sure that you all see ways to further simplify this, because the Q or not Q and the P or not P, of course that will be equivalent to true, but this is where the conjunctive normal form algorithm stops, and the rest is what resolution does for you. And it's not always that straightforward as in this example. Yeah? All clear? Yes?
Conjunctive normal form is unique for a certain formula, right?
Good remark. Yes. This one isn't actually unique. In a really strict sense of the word normal form, it should be unique. Then actually you have to do something more to this formula, because now you can certainly give another conjunctive normal form according to this definition, which is logically equivalent to this one. Good that you say so, but this is where we stop right now.
Okay.
Okay. Right. So now, the important part is that you realize this conjunctive normal form thing, and that you keep in mind that we're going to interpret them as sets of literals. Now I'm going to do something else to those sets of literals to simplify them. And there are sort of obvious ways to simplify them, there are less obvious ways to simplify them. Here actually in this particular example there is an obvious way which we already saw. If I write this as a set of sets of literals, it becomes a set P, Q, P bar, comma, Q bar, Q, P, and there you have a special case where, actually in this case, both of those clauses have a proposition and also its negation. And I think that all of you agree that such a clause doesn't mean doesn't add any information to the whole thing. You might as well remove it from your formula or from your clausal form without changing the meaning of the thing. Yes? So one simplification certainly is to get rid of all clauses that have both a literal and its negation. But there are more simplifications, and in order to introduce you to you those other simplifications, I need another notion which is different from the ones we've seen before, which is, I call this co-satisfiability. This similarity symbol will stand for co-satisfiability. That's a kind of similarity, but it's not the same as logical equivalence, because now the two things will be called co-satisfiable if one is satisfiable, if and only if the other is satisfiable. But what I do not require here is that they have the same set of satisfying models. Just want them to be satisfiable, or both not satisfiable. Okay, this is slightly strange. The existence of a model is preserved, but if I have two formulas that are co-satisfiable, they don't even have to have a single model in common. Their sets of models might even be disjoint. Here's an example. P is co-satisfiable with not P. Because one has a model if and only if the other has a model. Indeed, they both have models, so it satisfies the criteria for co-satisfiability. But of course, the models of P are disjoint from the models of not P. So I have two formulas. They are equivalent in this particular sense, but they don't have a single model in common. And it's much weaker than this logical equivalence, because logical equivalence requires that the sets of models are the same. I mean, it does imply, this logical equivalence does imply that two formulas are co-satisfiable. Because if their sets of models are the same, then it is certainly the case that one has a model if and only if the other has a model. The same models. Yeah? Yes?
I think I don't really understand why is P co-satisfiable to not P.
The definition of co-satisfiability says that one must be satisfiable if and only if the other is satisfiable. So if I give you the formula P and ask you, is this satisfiable or not? What will your answer be?
Yeah?
Yes, it's satisfiable. If I ask the same question of not P, of course it's also satisfiable. Yeah. So it is the case that one is satisfiable if and only if the other is satisfiable. Namely, they are both satisfiable. So it's a bit of a very strange, trivial case, but it certainly satisfies the definition of co-satisfiability.
Okay, but it's not that if you have a formula that's not co-satisfiable to the negation of the formula.
It's certainly not always the case that a formula is co-satisfiable with its own negation. No, this is only for that particular case, because if you have a valid formula, yeah, then its negation will be unsatisfiable. So then the formula is satisfiable because it's valid, yeah, and the other negation will be unsatisfiable. So, yeah, but in this particular case, it holds. So why do we even want to look at such a strange notion? Okay, more notation. L, this is the letter L and not the letter I. I'm sorry for the sans serif font in this case. You cannot really distinguish it easily. This is a literal. This will be the converse of the literal. So if the literal is some, for instance, P, then its converse will be not P, and if the literal itself is not P, then its converse will be P. And I will also use one more symbol, the box. The box will stand for the empty clause. Remember, a clause is a set of literals that is interpreted disjunctively. And now I'm talking about the empty set of literals. So, what does that mean? Is that always satisfied or is that never satisfied?
It says unsatisfied.
Yeah, I gave the answer away. True, but can you see that this is the correct extrapolation? Yeah, if you take a lot of ors, then every time you take away one of those ors, the number of possibilities grows smaller to still satisfy the rest. And once you take out the last option out of that set of ors, there's no way you can satisfy what is left. I mean, nothing's left. It's simply equivalent to false. So the empty clause is equivalent to false. Okay. Here are some rules for simplifying a conjunctive normal form modulo co-satisfiability. I'm going not to present all of them, but to give you an idea going to present some of them. Here it says, okay, my conjunctive normal form is this set of sets of clauses. It's called S. So if I take the union of that set, that's simply all the set of sets of literals. Sorry, the union of S is simply the set of all literals appearing in my clausal form somewhere. So if L is a literal occurring in my clausal form somewhere, and the converse of L does not appear in my clausal form anywhere, then, well, think of it. I have a lot of ors, and one of these clauses has a literal in it, and the converse of that literal appears nowhere. Then I could just set that literal to true, yeah, without penalty, because its negation doesn't occur. So if I set that literal to true, then all the clauses in which that literal appears are true. Yeah, because one of the ors is then satisfied. There's no penalty. All the other clauses still can be true or can be false, but whatever else, just removing all the clauses that contain that particular literal will not change the satisfiability of my clausal form. Okay, here's an example. I have this clausal form over here, and here I have a literal R that occurs positively in two of the clauses and negatively nowhere. So my claim is I can remove all the clauses